Welcome back to the deep dive. Today we are taking on, well, the ultimate concept of nothingness.
Yeah, empty space.
Exactly. If you look out into the vastness of space, the void, the vacuum, your instinct tells you it's empty. I mean, that's what hundreds of years of classical physics taught us.
For sure. It's just nothing.
But our stack of source material today, it pulls back the curtain on quantum mechanics,
Mm-hmm.
and it reveals a truth that is, well, it's far stranger and infinitely more active. We're diving into the hidden reality of the vacuum, asking, is there really such a thing as empty space?
That's the mission right there.
Yeah.
Today we're trying to understand the physics of the invisible. Specifically, this one concept that sounds like science fiction, but it's absolutely real: virtual particles.
That's virtual particles.
These are temporary, fleeting ghosts that fundamentally shape the universe.
Yeah.
They prove that what looks like nothingness is actually a high-energy, really chaotic environment.
A ghost party.
This deep dive is about the quantum party happening right under our noses.
Okay, and that gets us right to the big roadblock, the thing that I think confused physicists for decades, and our sources really hit this head on. It's the word virtual itself.
Right.
When you hear that, you think, not real. Maybe it's just a mathematical convenience, or as one source playfully put it, a figment of imagination, or even like something digital, Photoshop.
And that's the natural reaction. If they're not real, why are we talking about them?
So why are we?
Because they exist in that strange duality at the heart of quantum physics. They're called virtual because you can't directly observe them, not like a stable electron or a photon. They appear for these incredibly short moments, and then poof, they're gone.
It's just gone.
Instantly. They are so fast, so fleeting, that the universe itself seems to just shrug and say, you didn't catch me, goodbye. They exist just long enough to influence reality, but not long enough to get caught breaking the rules.
Okay, let's unpack that last part. How can something just appear and disappear? Doesn't that directly violate the conservation of energy?
The big one.
The most fundamental rule of classical physics: energy can't be created or destroyed. So if particles, which are just mass and energy, are popping into existence from nothing, where's the energy coming from?
This is where we get the crucial loophole. It's from the Heisenberg uncertainty principle. Classical physics, it demands perfect energy conservation all the time. But the uncertainty principle, it has this energy time formulation that says, well, it says you can briefly borrow energy.
Borrow it.
You can borrow an amount of energy,
Right.
E, as long as you return it really, really quickly in time t. The shorter the time, the more energy you can borrow.
So if you want a lot of energy to suddenly create, say, an electron and its antiparticle, a positron,
You have to make sure their existence is impossibly short.
how short are we talking?
Tiny fractions of a second. So short, they fall way below our ability to even measure them. So this brief, temporary violation of energy conservation, it's perfectly fine under quantum rules. The moment they're created, they have to annihilate and repay that debt.
So they give the energy back to the vacuum.
Exactly. They are temporary, but they are absolutely essential to how every force in the universe works.
Which leads us right into section 1, the actual mechanism. We think of space as, stable, static. But you're describing something really chaotic. How do the sources describe this environment where virtual particles are born?
Well, they describe the quantum vacuum as fundamentally not empty. It's not a void at all.
It's full of something.
It's full of potential. To get across the intensity of this energy, the sources use this fantastic analogy. They described it as a magical cauldron.
A magical cauldron. I like that.
That is constantly boiling, and it contains this immense, untapped amount of energy.
It's just churning away. And inside this cauldron, you've got pure energy spontaneously converting itself into matter and antimatter. Can you walk us through that pairing process again?
Sure. So the energy, it spontaneously transforms into a pair of particles. You get one standard particle, let's say an electron, with its negative charge.
And its opposite.
And its corresponding antiparticle, a positron, which has a positive charge. And this happens constantly at every single point in the vacuum.
Every single point.
They exist for that fleeting borrowed moment before they quickly collide and annihilate right back into pure energy. The cycle is just incredibly rapid.
So the vacuum isn't passive at all. It's this intense, frantic churn of creation and destruction. If we could zoom in, what we'd see is basically what the sources call a ghost party under the microscope.
That phrase really captures it.
It does. But if this chaos is happening everywhere all the time, why does the macro universe, the table, this chair, why does it all feel so solid and stable?
That's the core question, isn't it? The reason our world seems so stable is that while energy is violated locally and for a moment, that debt is always paid back instantly.
So on average, it balances out.
On average, over any time you can actually measure, the vacuum is in perfect energy balance. The particles are virtual precisely because they exist for too short a time to be measured as permanent mass or energy.
But you can measure their effects.
Yes, it's only when we introduce extreme conditions, like putting two metal plates very close together or looking at a black hole, that we can actually see these temporary ghosts have a real, permanent, and measurable impact.
That sets up section 2 perfectly. I mean, if these particles are just ghosts that average out to zero, why should we care? How do we know this isn't all just, theoretical math?
We care because these virtual particles, they have profound, measurable, real-world effects. And these effects are the experimental evidence. They validate their existence. They prove the quantum vacuum is a real physical thing.
It's not just empty space.
It's a medium. It exerts pressure.
Okay, let's start with the first piece of proof, the one that's almost impossible to reconcile with classical intuition, the Casimir effect.
This is such an elegant and famous experiment. It was first theorized back in 1948.
And the setup is pretty simple, right?
Deceptively simple. You take two neutral, uncharged metal plates, you put them incredibly close together in a vacuum.
Okay.
Now, if the vacuum were truly empty, nothing should happen. The plates should just sit there.
But they don't.
They don't. What scientists measure is a tiny but definitely measurable force pushing those plates toward each other.
And that force is generated by virtual particles.
Precisely. Let's try to visualize it. You have the two plates separated by a tiny gap, maybe just a few hundred nanometers wide.
Super small.
In the space outside the plates, virtual particles of all possible wavelengths can pop into existence. They're like waves in this quantum ocean.
So any size of wave can exist out there.
Exactly. But between the two plates, the situation is different. Because that gap is so small, only virtual particles whose wavelengths can fit neatly inside that tiny space are allowed to form.
So it's like a filter. The plates act as boundaries that exclude the longer wavelengths. The bigger, more energetic virtual particles just can't form in there.
That is exactly the nuance. So the density of virtual particles, the number of possible wavelengths, is lower between the plates than it is outside them.
Which creates an imbalance.
A quantifiable imbalance. The constant frantic pressure from the virtual particles outside the plates is greater than the reduced pressure inside the gap, and that pushes the plates inward.
That pressure is the Casimir force.
That's it. It's direct, tangible proof that the quantum vacuum isn't empty. It's a high-pressure environment.
The invisible is pushing the visible. And this isn't just theory, right? This is something engineers have to deal with.
Oh, absolutely. In microengineering with microscopic machines, the parts are so close that this force becomes really significant. You have to account for it.
Incredible. Okay, let's go from the small scale to the largest, because the second effect is just, it's cosmic. It's paradigm shifting. Hawking radiation.
The connection between virtual particles and black holes is, I think, the most shocking implication of the whole theory. You said it earlier. These fleeting, temporary particles are what cause black holes to evaporate.
It just sounds impossible. Black holes are the universe's greatest consumers. Nothing escapes. So how can a little bit of quantum mischief undo the most powerful gravitational forces in the cosmos?
The whole thing happens at the most dangerous boundary in the universe. The event horizon.
The point of no return.
That's the edge. So we know these virtual particle pairs are appearing everywhere, all the time. But the key is when a particularly antiparticle pair pops into existence right at the event horizon of a black hole.
They appear, just like everywhere else.
But because of that intense gravitational field, something extraordinary and permanent happens before they can annihilate each other. One particle, say the antiparticle, gets pulled across the event horizon. It falls into the black hole.
And its partner?
His partner, the other particle, is left isolated on the outside. It lost its chance to annihilate, so it escapes. It flies out into space.
Wait. If one falls in and the other escapes, they can't annihilate. They can't pay back that energy debt. So the escaping particle is now effectively real. It's permanent.
Right.
So where does the energy for this now real particle come from?
This is the genius of Stephen Hawking's insight. The energy debt has to be paid. And since the escaped particle can't provide it, the energy is stolen from the black hole itself.
From the black hole's mass.
The particle that falls in is theorized to have negative energy relative to us, a distant observer. So when that negative energy particle crosses the event horizon, it actually subtracts mass energy from the black hole.
So the creation of that escaping real particle is directly financed by the black hole's own mass dwindling away.
Exactly. That escaping particle is the radiation-Hawking radiation that we would measure leaving the black hole. And over vast, vast periods of time, this constant process turns the black hole's mass into escaping energy.
And it eventually just evaporates.
It evaporates. The universe's ultimate destroyer is undone by the constant, invisible quantum chaos happening right around its edges.
That is just mind-bending. The universe's most destructive, most permanent objects are dismantled by something that's fundamentally temporary and invisible. It forces you to recalibrate your entire understanding of power and stability.
And this connects us back to the bigger picture, which is just the sheer scope of all this quantum activity. Scientists describe it as a very small, constant flash, and it's happening at every single point in the vacuum, nonstop, every moment.
We're not talking about something rare out in deep space.
No, we're talking about the background state of all reality, including the space right here between us.
And this activity is what governs the fundamental forces of the universe. Electromagnetism, the nuclear forces, they all rely on exchanging different types of virtual particles to transmit their influence.
Which means the very cohesion of matter, the stability of the atoms that make up our bodies is dependent on this ghost party.
Right.
It makes you appreciate that what we see as stability is really built on a foundation of profound, rapid, invisible chaos. Honestly, reading this material, I had the same thought as one of the sources. When you understand this quantum reality, concepts from Marvel movies suddenly seem, well, commonplace.
Or at least plausible.
Yeah. Thinking about alternate dimensions or invisible energy fields, that stuff is less strange than the idea that the physical gap between your fingers is a high-energy field where matter and antimatter are generating and destroying themselves faster than light can even travel across it.
It makes our perception of reality look like a slow-motion video of a much, much faster process.
It really does. And if we look at the core lesson from our source material, it's this. A huge amount of what actually holds the cosmos together can't be seen. It's described as virtual, yet it is present, and it operates with full power. This invisible framework is the engine.
An incredible synthesis. So let's just quickly review what we've uncovered. We started by defining virtual particles as these temporary ghosts, allowed by the uncertainty principle to briefly borrow energy. We established that the quantum vacuum is not empty, but this magical cauldron constantly boiling.
Creating and annihilating.
And finally, we saw that these invisible particles have two profoundly real effects. The Casimir Effect, where they physically push plates together, and Hawking radiation, where they cause black holes to slowly evaporate by stealing their mass.
And that brings us to the final provocative thought to leave you with. We started this whole thing by challenging the idea of empty space.
Right.
We now know the space all around us is high energy, it's chaotic, it's governed by these invisible temporary fluctuations. The most active, powerful forces in the universe are fundamentally temporary and invisible.
So if the most powerful engine of the universe relies on this constant creation and annihilation, if reality itself is built on borrowing and repaying this energy debt, what does that imply about the stability of the things we can see and touch?
Consider that constant, quiet struggle happening in the vacuum right now, that incredible force from these ghost particles. It's a powerful reminder that our perception of a solid world is just the surface. It's a manifestation of constant, frantic, subatomic activity. The space around you might not be empty, but it is certainly never static.
Yeah. The ultimate ghost party.
And it's running the cosmos.